Hi dear students, in today's class let's learn a new lesson of physics part, that is magnetic effect of electric current. This is the chapter number 13. So in the previous chapter on electricity we learned about the heating effect of electric current. What could be the other effects of electric current? We know that an electric current carrying wire behaves like a magnet. That is, when the current passes in the wire, it also behaves like a magnet. Let us perform the activity to reinforce it. That is the deflection of a magnetic compass needle by a current in a wire. Okay, so this is the simple circuit. Here the copper wire, it is connected to the battery and to the switch, and also the magnetic compass, it is kept parallel to the wire. Okay, so what happens, let's see, when we on the switch. Yes, the compass needle showed the deflection, right? It is showing the deflection. So why it happens? Why it shows the deflection? Because of the current in the conductor that act like a magnet. That means here the magnetic field is produced. So what did you observe? It is observed that when current passes in the wire, needle deflects, and we can conclude that a current carrying wire produces magnetic field which deflects the magnetic compass needle. Thus, we can say that electricity and magnetism are linked to each other. Then what about the reverse possibility of an electric effect of moving magnets? So in this chapter, we will study magnetic fields and such electromagnetic effects. Cleared? Okay. See, here you see a bar magnet, right? Bar magnet has two poles, north pole and south pole. The end pointing towards north is called north pole or north seeking. The other end that points towards south is called south pole. Okay. So the bar magnet has two poles, north and south. And here you can see a compass needle also. Okay, so compass needle also behave like a magnet, and always south and north pole attract each other and south pole repel each other. That is, like poles repel while unlike poles of magnets attract each other. Let us understand this through a small activity. Okay, this is the compass and the needle is there in the compass. When we keep close bar magnet to the compass, the needle shows the deflection, but the north and south pole attract here each other and the north and north pole repel each other. You can see this. So through this activity we can infer that the like poles repel while unlike poles attract each other. Okay, so this is about the bar magnet and compass needle. So we can infer that compass needle is also a small bar magnet. Okay, and the ends of the compass needle point approximately towards north and south direction. Okay, now let us understand the magnetic field and field lines. Before that, let me show a small video of the activity, that is activity 13.2. Okay. Fix a sheet of white paper on drawing board using some adhesive material. Place a bar magnet in the center of it. Now sprinkle some iron fillings uniformly around the bar magnet. Okay, now tap the board gently. So what do you observe? Yes, the iron fillings arrange themselves in a pattern. Why do the iron fillings arrange in such a pattern? What does this pattern demonstrate? Yes, see, you can see the bar magnet here, and around the bar magnet there is a magnetic force. Okay, the magnet that exerts its influence in the region surrounding it. Therefore, the iron fillings experiences a force, and the force thus exerted makes iron fillings to arrange in this pattern. Okay, so we observe that when the board is gently tapped, the iron fillings near the bar magnet align themselves along the field lines. Then what do we call this region that is near the bar magnet? That is magnetic field. Okay, the region surrounding a magnet in which the force of the magnet can be experienced is called magnetic field. That is, this region is called magnetic field. Okay, yes. Then what are all these lines represents? These lines are called magnetic field lines. Okay, the lines along which the iron fillings align themselves are called magnetic field lines. So these all are magnetic field lines, and this region is called magnetic field. I hope this is cleared. Now let's see the properties of a magnetic lines of force. What are the properties of these magnetic lines? A magnetic field lines originate from North Pole and ends at its South Pole. Remember here, the magnetic field lines always emerges from North Pole. Okay, and it merges at South Pole. From North Pole, it moves from North Pole to the South Pole. That is the first property. The next is, a magnetic field line is a closed and continuous curve. So why it is closed continuous curve? Because the direction of the field lines is from its south pole to its north pole. So the magnetic field lines are a closed curve. Okay. The next property, the magnetic field lines are closure near the poles of a magnet where the magnetic field is strong, and farther apart where the magnetic field is weak. That means near the magnet the field lines are strong. As we move away from the bar magnet, these field lines it becomes weak. The field lines becomes weak. The fourth one, the magnetic field lines never intersect each other. These lines never intersect, never meet at a point. Why? So what happens if they meet at a point? Yes, if two magnetic lines of force intersect, then there will be two tangents and hence two directions of the magnetic field at the point of intersection. So this is not possible. Okay, see here, if these two lines meets at a point, we will get two tangents. This shows the two direction of the magnet, but it is not possible at all. Therefore, the field lines never intersect each other. And the last point, a uniform magnetic field is represented by parallel and equidistant field lines. Always these field lines are parallel to each other and they are at the equidistant. Okay, so these are the properties of a magnetic field lines. Let's recall once again. This is important First one, a magnetic field lines are originate from north pole and ends at its south pole. The second one, the magnetic field line is a closed and continuous curve. Then the magnetic field lines are closer near the poles of a magnet where the magnetic field is strong and farther apart where the magnetic field is weak. The magnetic field lines never intersect each other. A uniform magnetic field is represented by parallel and equidistant field lines. Now it's time to give you question answers. The first one, why does a compass needle get deflected when brought near a bar magnet? Yes, when we keep a bar magnet near to the compass, the needle shows deflection. Why? Because the magnetic field of the magnet exerts force on both the poles of the compass needle. The force experienced by the two poles are equal and opposite. These two forces from a couple which deflects the compass needle. Because the bar magnet exerts force on both the poles, north and south pole, and due to this the needle shows the deflection. And the next question, these question answers are homework. Draw magnetic field lines around a bar magnet. So you refer the figure 13.4 page number 119. Draw that diagram for the second question. Then list the properties of magnetic field lines, that is 5 properties. Then 5 properties you have to write. Last one, why don't two magnetic field lines intersect each other? That answer is also given. You go through the slides and write the answers. And the last, this is one small activity. The answers of these questions are discussed in the upcoming classes. Okay. So identify the poles of the magnet in the given figure. Here 3 figures are given. In this you have to identify the poles. For example, in the first figure, that is P and Q, magnetic fields, the lines are coming out from the poles, right? So this is north pole, P and Q, and they repel each other. So P and Q are north poles. Similarly, for the figure 2 and 3, find the poles. Okay, thank you.